Hello everyone, I'm Soyeon Park from Georgia Tech. Today I'm giving a talk about fuzzing JavaScript engine with aspect preserving mutation. So these days, everyone may use web browser to send email, transfer money, and find information on the web. In this graph, around 4 billion users are using web browser in the world. As every major web browser embeds JavaScript engine inside, it means a huge number of people will be affected if the JavaScript engine has a security critical bug. To make it more interesting, let me make a story. Let's assume that a user wants to check our paper information on my website. So he entered the web URL and get the website. To get the information about SMP conference, he clicked the hyperlink, which should let him go to the conference website. However, this one click makes his laptop being hacked so that it leads to leak sensitive data such as password, bank account, and private data because hacker can gain control over his laptop. To share another indicator to show the severity of JavaScript bug, we collect the last 4 years Pontoon result, which is the top industry hacking competition against major commercial software including web browser. Among the 11 successful trials to hack the major four browsers, Edge, Safari, Chrome, and Firefox, 9 bugs utilize JavaScript vulnerability to get the remote code execution. So I guess we all understand how severe it is in the wild. However, finding JavaScript bug is hard in reality because of several reasons. First of all, JavaScript engine codebase is very large. The smallest one, JavaScript core for Safari, has written almost 450K code, and the largest one, SpiderMonkey for Firefox, has 1 million. And many of bugs found recently is going to deep code paths more and more. For example, JavaScript engine is consisted of parser and interpreter in high level and several layers of JIT compiler and executor. Many of simple bugs located on parser and interpreter can be found by simple API fuzzing. However, most bugs in recent days are located on JIT compiler like due to the wrong optimization. To show the trend of recent bugs, we collected recent reported security bugs in ChakraCore from 2016 to August 2019 from the Google Project Zero Issue Tracker and ChakraCore security patch. The graph shows that parser, interpreter, and memory corruption bugs relatively considered as simple and shallow bugs are decreasing, but out-of-bound and type confusion bugs on JIT compiler, which is considered more complex, and deep bugs are increasing. So finding JavaScript bug like a small number of expert human hacker is definitely not easy. Here are two POC codes for CVEs, motivating us that payload can have a similarity even if the root cause of the bug in code level is totally different. Both POC are written by same hacker so that it looks similar. The second box needs special conditions and variation to be discovered. First, both has for loop as precondition to trigger JIT compiler, and also pass empty object as parameter to trigger wrong JIT optimization. Then both POC calls the JIT function OPT again with different parameter, which all have side effects for different reasons, but has the same function type. Third, the order of instruction in JIT function is important to lead wrong optimization as well. However, the second bug includes more variation that the fuzzer can be good at. From this example, we get the idea that getting key factor from the existing bug and combining them with a variation generated with fuzzy way can make a good result. So we code the key factor as aspect, which are embedded in the POC of existing bugs and help to guide to discover new bugs. Here is a type confusion bug which makes the zero index value of the array to object type from float type. For example, this POC has three aspects we think important to lead the type confusion. First is the assigning float values to an array and the order of instructions as it triggers wrong JIT optimization. Next one is the for loop invoking JIT compiler. And last one is the arrow function to assign object value to the same array, which leads the main reason of the type confusion. So we propose DIE, a fuzzing framework which has its own strong generation engine and mutation engine, which preserve aspects of the existing bug. In the big picture, DIE is consisted of three parts: preprocessor, input generation, and executor. Let me introduce one by one in further slides. The first component, the original seeds are conveyed, is preprocessor. It instruments the original seed to get the type of identifier in the seed dynamically. With the type information generated by the dynamic analysis, it produces AST, which has type information for every node. Then the typed AST is passed forward for input generation. In detail, our dynamic analyzer instruments corpus to record type per each line. For example, at the first record type function call, our type information box is empty. However, at the second function call, it records the type of variable n as a number. And at the last function call, it also records the array type and the number arrays. It's possible because DIE maintains more fine-grained type system than JavaScript itself. At the end, every record of type information is gathered and sent to further process as type information. This information allows us to get every object and its type information for each line so that we can get a more precise object and type information in specific scope and context. Further, we need a static analysis to make every AST node have type information. From the previous analysis, we get the type information of the corpus, but it only includes the type of identifiers. So we propagate the information from bottom to top based on custom rules. For example, number type will be assigned to the array indexing operation node, as the variable A is number array. Special nodes which we don't want to change will be assigned to immutable type so that the further mutation engine will not choose this node to mutate. Next step is input generation, which uses the typed AST as input and return JavaScript file. DIE generates the input with generation engine and mutation engine, but our mutation engine has a special feature called aspect preserving. To maintain aspect of existing bug, DIE preserve type and structure during mutation. For example, in the previous bug example, the type of identifiers such as float, array, function, and object type will be maintained during mutation. In addition, the order of the instructions and control flow related statements such as for loop will be preserved as well. Let me explain the detail of type preserving mutation. DIE first gets the typed AST and type information from the previous process. In this example, we want to mutate the marked number type. Then the generation engine will generate typed AST node, which is a number type, by utilizing existing identifier in the context. In this example, it produced array property and array indexing as a number type. For this, our generation engine maintains type information of parameter and return value of JavaScript API, and type information of properties for every type of object. Finally, mutation engine replaces the existing node in the typed AST to the generated type node like the figure. While type preserving is focusing on what to mutate and how to mutate, structure preserving is more about what not to mutate. The mutation engine selectively mutates nodes to avoid breaking existing control flow. For example, the mutation engine can choose any node in the AST to mutate it except the immutable type. At the final stage, I execute the mutated JavaScript file with instrumented JavaScript engine in the distributed fuzzing platform. During execution, if the seed reaches new code path, it returns the updated code coverage information to the input generator as feedback. If it reaches crash during execution, it will report it. Die is mostly written in TypeScript. Few framework harness is written in Python and shell script, and small modification on AFL to adopt code coverage feedback routine. In total, it has written in nearly 90K lines of code. In this section, I will show the evaluation results fuzzing JavaScript engine with Die in the wild, and extra information which stand for the techniques we implemented on Die. To test Die with commercial browsers in the market, we ran it up to 3 weeks against 3 major JavaScript engines used for Microsoft Edge, Apple Safari, and Google Chrome. As a result, we got 48 unique bugs in total. Among them, 39 bugs has been fixed, and 11 bugs are acknowledged as CVE because of their severity. Also, we got 27K US dollar as bug bounty reward. To show the effectiveness of a reversing aspect for finding bugs, we manually checked 84 distinct crashes and 28 unique bugs in ChakraCore. As a result, we observed that 50% of found bugs and 48% of crashes are seriously affected by structure and type preserving. In total, more than 90% of found bugs and crashes are affected by our aspect preserving, which means that you cannot reproduce 90% of the bug if you eliminate the market structure or ignore type information in the generated seed. Here is one example bug we found. It was generated based on existing CVE in 2018. Although it looks simple modification from the seed, it can be invoked because of our strong generation engine and aspect preserving mutation. In the example, these green statements are generated with type information as we can know the type of the variable start is number and the type of the variable ARR is float array in the scope. Next, the if statement and the for statement should be intact to invoke wrong JIT optimization. Also, the small modification from number 3 to variable I can happen because of type preserving mutation. To evaluate the aspect preserving of die, we use the ratio difference of JIT optimization phase invocation between the generated inputs and seed file because we believe the difference can indirectly represent how many aspects are devastated. As a result, die maintains JIT optimization pace invocation 1.53 times more than die without structure preserving, which shows that the structure preserving helps to maintain aspect well. Also, Code Alchemist shows 4.29 times more differ from the original because it breaks corpus as code fragment, and the aspect will be broken during the process as well. Superior shows negligible difference from die. It is because Superior is also mutation-based fuzzer, and it tries to mutate things in grammar-based way. To show the power of our generation engine, we evaluated the validity of generated input by counting runtime error rate of generated input. The result shows that die generated 2.31 times more valid input than Superior and Code Alchemist, and 2.42 times more than JS FunFuzz. In detail, Superior generates many syntax error-prone input, which shows that its mutation rules includes a lot of grammar error, although it mutates based on grammar rules. Also, Code Alchemist generates many reference error and type error, which means that their type and scope analysis might not work well. JS FontFox produce three types of error on similar ratio, which shows that its generation rule is not well implemented. Although Dye also generates more error-prone input than vanilla, which is original corpus. However, we figure out that it is because covering feedback makes invalid input to the queue so that the invalid input continues to be used. To evaluate our generation engine in precise way, we turn off the code coverage feedback routine and reevaluate it. The result shows that it produces less error rate than vanilla. As a final, we compared the number of unique crashes Dye and the other state-of-the-art fodder suites for 24 hours. Dye reaches more crashes than Superior and Code Alchemist during the same period. One interesting fact is that Dye reaches more crashes than Dye without structure programming as well, which shows that restricting fuzzing somehow can be helpful to find more bugs. To sum up, Dye is a JavaScript engine fodder that preserves the aspects from POC of existing bugs achieved by type and structure preserving. And we discovered 48 unique bugs with 11 CVE assigned. And we will open source our project in this link. Thank you for listening.